Okay, so in this morning session, we're going to do a very quick intro to the basics of recursion, and we'll do a few very simple examples. At the end of it, you will probably be kind of struck with the main question, which is why do we ever use recursion? Because a lot of the problems we're going to talk about this morning that we solve with recursion are actually able to be solved without recursion. So we can use other ways to do. So we can use traditional for loops or other kind of methods to do these problems. And it may seem like recursion makes life harder than it has to be. And the short answer here is just because, yeah, most recursion questions can be solved with other methods, but in the afternoon sessions, we'll actually see a few examples of recursion problems that actually require recursion. A traditional for loop just won't cut it. So in the morning, we kind of lay out the very basics, and then in the afternoon, we drill a little bit more into the more complex use cases. So the definition of recursion, and I'm sure you might have seen this in other places, is pretty much when a function calls itself. Now, that's not really helpful in terms of us understanding what it's actually doing, but it's a little more helpful to understand kind of when do we like why people use recursion. Okay, so recursion is a form of looping, and all that means is whenever you use recursion to solve a problem, it means you want to do something many times. Okay, the reason why recursion can be a bit easier to think about is because it actually does a very good job of breaking big problems into smaller chunks. And I think that second bullet is, it could be a matter of opinion, but really that third bullet is it won't negatively affect performance too much. That's actually one really big advantage of recursion in some instances. Oh, sorry. That's one reason why sometimes people don't use recursions nearly as much is because recursion actually, and we'll talk about this when we talk about the call stack. Recursion actually does hold a lot in the memory simultaneously. So just from a technical background perspective, recursion sometimes can be used because it's simpler because it breaks down big problems. But also it can be a bit heavy on the computer. Now, that doesn't mean it does necessarily more total calculations than any other method. But as you see, what recursion does is it actually holds all of it in memory more, right? It juggles more processes simultaneously. Yep. Okay. So so before we talk about like how to use recursion and what it looks like, we have to kind of do a quick primer on something called the call stack. JavaScript runs synchronously, so SYNCH. I don't know if you type it down here, okay. But anywho, but it's a single threaded process, which means only one function can run at a time. In fact, this is actually a really powerful assumption around programming that we use in JavaScript, really for the entire bootcamp so far, but we never really talked about, right? And that's this idea that everything in JavaScript more or less runs in sequence top down, and more importantly, no line of code can run unless the previous line of code has finished running, right? Like whenever we step through a function, we take it for granted that line one has to finish running before we start line two, right? So that way, if I declare a variable on line one, by the time I get to line two, it means that variable has been declared and I am able to use it. This is not the case in every programming language, and that's a bit of a more heavy discussion for another day. But on line three there, right, we see that's what single threaded means is there's only kind of one thread, as in like almost it's almost like there's only one line. Everyone has to go through that one line, and so therefore there's a very clear order of what happens first, then what happens next, then what happens next. So at any given point, we kind of know what JavaScript is working on. The call stack is just a conceptual implementation of that principle that at any given point we know what JavaScript's working on, and more importantly, we have a list of all the tasks that JavaScript, or rather, we know what JavaScript is working on now, and we have a clear list of what tasks JavaScript has to do next, right? Because once again, because it's a we'll say linear or a single threaded process, it means step one has to finish before step two runs. Okay. The best way that people sometimes describe a call stack is they describe it as either a stack of pancakes, or another analogy I like a lot is it's a stack of plates at a buffet line. If you've ever been to a buffet, what that looks like from a graphical perspective is if we look at this code on this page, right? We have a function called first that console logs out IM first. We have a function called second that console logs out IM second. Okay. On line 13, we reach this line called first, and we execute that function. When we do that, we essentially add the first function to our call stack. That means to the computers, or that means if you're that means that if you're the computer and you look at it from the computer's perspective, that means when we get to line 13 at a point in time, the computer will prioritize all of its resources slash the one thing that is working on at that moment is finishing executing the first function. Okay, it executes the first function, it console logs out IM first, and after we're done with the line of code, we take it off our call stack, right? It's almost like a to-do list. We take it off our to-do list because we finished the task, and then we move on to the next line, which is line 14. Here, we now then put the second function, if you will, on our call stack on our to-do list. We run that line of code, it console logs out IM second, and now I am done with the page of code, right? Because after I take the second function off of my call stack, I've reached the end of my page. Okay, so that's a very quick example of how sequentially the call stack manages. Now, if I was to write a function like this, for example, it's called countdown. It takes a num. All we have in it is a simple for loop that starts at num, and then it says while num is greater than or equal to 1, we decrement num. So this means we're counting starting at, in this case on line 9, we invoke this function with 5. It means we start at I equals 5, and we work our way down all the way until I equals 1. Okay, and so if we put these two processes to get, Okay, so if we put these processes together, let's actually see how some of the functions that we've historically worked on, how they look in the context of our call stack. Okay. So here, if we go back to the previous example of first and second, we now have a function called first. And in this function called first, notice how we console log out IM first, but as part of this first function, on line 3 there, we actually also invoke another function called second. And then on line 4, we console log out first is finished. On line 7, we define what the second function is, same as before. And now when we get to line 11, all we do is we only ever run first. Okay. So if I put myself in the computer's perspective now, and if I once again try to run this first function from line 11, the first thing I do is I put my first function on my to-do list because I'm going to work on that. And on line 2, as I go through the first function on line 2, I console log out IM first. Okay, that finishes line 2. Only after I finish line 2 do I move on to line 3. Now, what line 3 does is I see it invokes the second function, which now means I now need to put my second function also on my to-do list. And the reason why we use the stack of plates at a buffet line example is because if you've ever been to a buffet line, the way that the plates work is if I have a stack of plates and I as a customer I come over, I want to grab a new plate, I usually grab the one that's at the top of the stack, right? Like I don't like go through all the plates and work my way and go grab the one at the bottom of the stack. I pick the one that's at the very top of the stack. Okay. And so the reason why that analogy is very apt here is because if we look at our call stack, we can imagine that as a stack of plates at the buffet line. The computer will always work on whatever is currently at the top of the call stack. Okay, because we build on top of one another, it always starts from the top. And so in this case, when we get to our second function there, the one that we're running on line 3, that's currently at the top of our call stack, now JavaScript says, okay, my priority is to finish executing this second function. Okay, notice how the first function does not get removed because we haven't finished running that function yet, right? In order to finish run the first function, we have to finish running the second function first. Sorry, that was a bit of a nomenclature, a little bit hard to talk about, but it essentially is the first function cannot be finished until we finish running line 3, which requires us to run the entirety of the second function. Okay, so if I go back to being computer now, and I see, okay, the second function is currently at the top of my call stack. I needed to finish running first, so let me finish running second. When I run second, all it does is it console logs out I am second, and now I'm done with running the second function. I can actually take it off my call stack. Only after that does the computer look back and say, oh, before I took this detour to work on the second function, what was I doing before? Oh, I was working on my first function. Great, let me pick up where I left off. Okay, where did I leave off? I left off at line 4, right? Because running the second function was part of line 3. I've now picked it up again in line 4, and I console logged out first is finished, and only then do I say, yep, I am now done with my first function, and I'm done with this page of code. Okay, this is all I mean when I say call stack. Is just that there's a sequence. There's an order in which JavaScript runs the functions, and most importantly, JavaScript will not run a line of code until the previous line has finished. And so the previous line says, hey, can you run this other function instead? JavaScript says, cool, yeah, I will prioritize running that function now before I finish running the initial function I was assigned to. Okay, so if we go back now to our countdown example and see how it looks now, right? If we were to refactor this solution, one way for us to write it would be to write a function called countdown that takes in a number and literally just console logs out that number. And if we want to count down from 5 to all the way down to 1, we could do something like this. Okay, notice how there are no loops, but obviously this is also very cumbersome and not very flexible, right? If the countdown was starting at 100, it's a lot of code writing for us. But the very basics of this is just to let you know that at every single iteration of this loop, we are doing the same exact thing, which is I give you a number, or I give this function a number, and the function prints it out. And on line 12, that comment, it says how do the argument change between calls? Well, between each instance of calling this function, all we're doing is we're taking the number and decreasing it by 1. Okay? So because every time we call countdown, we're decreasing the number by 1, now we get to see how maybe there's a way we can actually use recursion to solve this problem, right? Which is to say that instead of us manually calling countdown over and over and over again, why don't we have the function call itself over and over and over again, and every time it calls itself, it will decrease the argument that it feeds to the next call by 1. So how does that look? Something like this. Okay. So let's step through this through the lens of a call stack. Okay. On line 7, I still have my countdown function that still takes in a number. On line 8, I console log out the number, and on line 9, notice how I call countdown again, except now I do num minus 1. Okay, I call it with myself with the number minus 1. So what happens when I do countdown now? Well, on the very first instance, I do a countdown of 5. Okay. And as I step through this function, it's going to say, well, on line 8, we console log out the number. Cool. And on line 9, we then call countdown, but now it's num minus 1, so it's a countdown of 4. Okay. So now JavaScript takes a look at our call sign and says, okay, you just put countdown of 4 on my to-do list. Remember, I have not finished running countdown of 5 yet, right? I'm only able to say I finished running countdown of 5 after I finished line 9. And so right now I'm in the process of working on line 9. So while this line 9 is going on, while countdown of 4 is going on, I need to kind of keep countdown of 5 on my to-do list still. Okay. So if I look at countdown of 4, what does that do? Well, countdown of 4 on line 8, we then console log out the number, which is 4, and then that calls countdown of 3. Now we can kind of see how our call stack is growing, right? I can't say I finished running countdown 5 because countdown 4 needs to run before I can say I finished countdown 5. But I also cannot say that I'm done with countdown 4 because countdown 3 needs to run before I can officially say that I finished that. And so if I go down the sequence, countdown 3 is going to print out 3, which is then going to call countdown 2. It's going to print out 2, and then that's going to call countdown 1, which is going to print out a 1. But then, hopefully you see the pattern here, right? We actually just keep going, and we never really stop. And so this is, eventually, if we do this with a computer, on a computer, it's almost like the error we saw with a while loop, which is that the computer is eventually going to be like, hey, I've been doing this, millions of times. I'm not stopping. I think this is a mistake on your part. I will throw an error and say, can you fix the code, right? In this case, the error that actually says is actually a pretty good descriptor. If you read it there, it's called a range error, and the error message is literally maximum call stack size exceeded. So every computer, depending on how big your memory is, has a call stack of how much code it can run concurrently. And in this case, the reason why the error got thrown is because the computer says, okay, I have a call stack that can maybe handle, let's say, 1,000 functions at once, and you ran more than that. And at that point, I think there's something wrong with your code as opposed to something's wrong with my performance. Okay, so the question now becomes, okay, kind of like almost with a normal loop, right? We've now created a loop that is able to call itself over and over again, and it can change the input each time, but we didn't tell it when to stop. So how do we build that aspect of it in? Well, so that is a very, very important part of writing any recursive loop. When you're writing a recursion loop, we call it the base case. Basically, at what point do you stop? And I would almost say that every time you write a recursion, that should be almost what you start with. Is okay, I know, it's easy to call myself over and over again, but when do I stop, right? Like, what's my stop criteria? And so here we can actually write something like this now. We have our countdown function still. Now we insert this if clause. It says if num is less than 1, we console log out done. Else, we do what we did before, which was we console log out our number, and then we run the function itself of num minus 1. So now if we just do a little bit shorter example here, if we run countdown 3, let's actually see what happens. Well, initially when we start, we have our countdown of 3. Okay, as we go through this countdown function, is num less than 1? Nope, num is 3. So we skip the if loop and we go to the for condition, right? It takes us now back down to line 8. We console log out 3, which is num, and then it says, oh, by the way, before you finish running, the last thing you gotta do is you gotta finish running countdown 2. Okay, so great. So now we're on countdown 2. We go back to the beginning of our function and we say, okay, let's run countdown 2 now. Once again, we go to our we step into our code. The first thing the code makes us check to see is if num is less than 1. And the answer is nope, 2 is not less than 1. So once again, we go to our else clause. The else clause then says, let's console log out num first. Let's console log out 2. And then before you finish running, I need you to run countdown of 1, or 2 minus 1. So once again, our call stack is building up. We run countdown 1. We check, is 1 less than 1? Nope. So then we go to our else clause. We console log out 1. And then we run countdown of 0, right? Because we're doing countdown of num minus 1. We're doing countdown of 1 minus 1. And now we're at countdown 0. And now when we do our function one more time, we go through, the first thing it has to check to see is num less than 1. Is 0 less than 1? And the answer is yes, it is. Oh, great. In that case, we console log out done. We finish up with our if clause. And voila. We've reached the bottom of our countdown function, right? We've finished our countdown function for running countdown of 0. Hopefully ever see that, right? We've now, if I just call countdown of 0, it does the if check, and the if check is true, so it goes from the if statement, it console logs out done. It skips over the else clause, line 7 through 10, and now we've reached the end of our countdown function. So that's over with now. So now I can actually take countdown 0 off of my call stack. I finished it, right? There's nothing else to do. So then, as JavaScript says, okay, great, I finished one task. What was next? And JavaScript says, well, before I took a detour to do countdown 0, I was working on countdown 1. And the question now becomes, okay, great, what else is there to do in countdown 1? Well, in countdown 1, we were on line 9, right? We said, okay, now that we finished line 9, let's move on to the next line. And ta-da, we're done with that as well, right? There's nothing else to run from countdown 1. So we can take that off of our call stack. And we see the same pattern happening for countdown 2. And then finally, we can actually say, yep, we finished countdown 3 because we finished running countdown 2. Countdown 2 we finished because it was dependent on running countdown 1, which we also finished, and that was dependent on running countdown 0. And so as we finish these functions, you can kind of see the cascade effect coming back now. We finished countdown 3, and now we've reached the end of the page of code, and we can say we're done. Okay? And by the way, this phenomenon here, this is what we mean when we say that in one of the earlier slides, we talked about how maybe recursion doesn't do any more steps than traditional loop, but it does more of it simultaneously. This is what we mean, right? Notice how at this point in time, the computer is simultaneously balancing, or the call stack has simultaneously has kind of 4 tasks being executed at once, so to speak, right? If I did a normal for loop, then all it does is it was to say, great, print 1, done with that, next one, print 2, done with that, next one, print 3, done with that, next one, right? Like with the for loop, it runs everything one at a time in a very linear fashion. Here, by doing recursion, we actually kind of flood our call stack with all the things we need to run simultaneously. In most cases, most computers are powerful enough that this is not a huge issue. But just kind of from a theoretically performance standpoint, just know that this is what we mean when we say that recursion can be more memory intensive. Is that it's not that it's doing more work overall, it's just doing more work simultaneously, right? Like it's like I have a construction crew. Like if I ask them to build one house at a time over and do it for 10 houses versus saying, hey, can you build all 10 houses simultaneously, right? It's just kind of, like when I step back and look at their overall output, they're doing the same amount of work. It's just when I ask them to do it all at once, it uses up more resources at a certain point in time. Okay, I'll pause here. Any questions about the example? Oh, wow, I didn't pause at all. Oh, okay, any questions here?
Would you ever use a return function when you're doing recursion?
We absolutely will, and we will see that in the next example.
Okay.
Yep. Did my walkthrough of this make sense to everybody? I think that's the main thing I'm worried about, is just to make sure like everyone understood kind of the logic process as I step through this. As I said during day 1, right? Computers are very good at being highly logical. Like they're very good at being highly logical. So as long as you can follow the logic and step through a function, you will always be able to kind of figure out what's going on. And I think there's a question.
I was gonna ask, is it possible to have recursion like within recursion, if that makes sense?
Yeah, totally.
Okay.
Recursion is just calling a function within itself, so there's no limit on how often you can do that, right? As long as you can write a function that doesn't break and just needs to call itself over and over again, there's nothing wrong with that. Like as long as we get logically created, the computer will do that, and as long as your code is well built, then it should run perfectly fine.
Okay, thank you.
Cool. Were there any other questions? Okay, then let's keep moving because we do have a few other examples to go through. Once again, this is as a recap of the countdown we just walked through. 1, and this is super critical, like put this in bold whenever you write a recursion function, you always need a base case, right? It's almost like writing a while loop. You need to be careful about, you need to be very clear to your computer, when do you stop? And so the base case basically tells you, when do you stop? And then lastly, if you remember the other aspect of a while loop was, every time we do the loop, we kind of need to be moving closer and closer to the stopping point. The same idea applies here, right? Whenever you do a recursive function, typically speaking, the input or some aspect of it needs to be changing so that every time you run it, you're getting closer and closer to your base case. You're getting closer and closer to your stop point, which makes sense, right? If you're not, then that means your thing's just going to run forever. And so, we'll talk a few examples about this afternoon, which like you might not know exactly when something ends, but you need to kind of directionally be confident that you are moving closer and closer towards the end. Okay, to whoever asked the question, recursion becomes more complicated when we return a value because we absolutely return values in most cases in which we use recursion. Yep. Okay, so let's take another look at another example called factorial. Okay. A factorial in math, so this is outside of programming. A factorial is just the product, so the multiplicative total of the factorial of a given number is basically that number multiplied by every number between itself and 1. Okay, so like 0 factorial is just 1. That one, just take it for granted. There's no, that's just like a mathematical thing. 1 factorial is just 1 by itself. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4, 3, 2, 1. Hopefully you see the pattern here. So that's what factorial does, okay? Now, if I was to ask you to build a factorial function using recursion, how do we do that? Well, first off, if I go back to the previous slide here, one quick thing that I really need to notice here is, when do I stop, right? Like, when does factorial end? And so based on my description of factorial, what I said was it's a multiplication total of every number between a self and 1. And so that means if I was to multiply every number between a number up until 1, well, eventually I stop at 1, right? Like, that makes sense. And so here, when I write this function, I'm going to start off by writing my base case. I'm going to say, okay, if you give me a number and say, what's this factorial? If you give me any number that's not 0 or 1, assuming we're only dealing with numbers greater than 0 here. If you give me any number that's greater than 0 or 1, if you give me like 15, I know I need to do some math. Okay, right? I know that if you give me a number that's not 0 or 1, I need to do some math, right? If you give me 2, I need to multiply 2 by another number. If you give me 5, I need to multiply by another number. However, if you give me 0 or 1, then I know that I just return 1, right? Like, that's the value. If I have a factorial function and you say, hey David, what's the factorial of 0? I'll say it's 1. I don't need to do any calculations because that's just mathematically what it is, right? Like, I know that as like a base condition. So if I do factorial 0 or factorial 1, I get back 1. Okay? We haven't used recursion yet, but we're just kind of setting our base case. We're saying, look, this is when you hit 0 or 1, it means stop doing math. The answer is 1. Okay? Now, how do we get closer to that? Well, one of the things that we noticed from just like the way that we drew that out from almost like a tree format is, well, what's 2 factorial? Well, 2 factorial is 2 times 1. Okay, that makes sense. What's 3 factorial? 3 factorial is 3 times 2 times 1. But we already know what 2 times 1 is, right? 2 times 1 is 2 factorial. If I look at 4 factorial, mathematically it's 4 times 3 times 2 times 1, but we already know what 3 times 2 times 1 is, because that's just 3 factorial. And as part of 3 factorial, we know what 3 factorial is because 2 times 1 is 2 factorial. And so you can kind of actually see this pattern unfolding where the factorial of any number is just the number itself multiplied by the factorial of itself minus 1, right? 4 factorial is 4 times 3 times 2 times 1, so 5 factorial is just 5 multiplied by 4 factorial. Everyone with me so far still? Right? Like this actually helps us kind of conceptually think about it in a different way. It's like, when I look at 5 factorial, I don't need to figure out what like everything else is. I just need to know what the factorial of 4 is, right? Because I multiply that by 5 and voila, I have 5 factorial. Similar, if I was someone said, what's 4 factorial? All I have to say is, you know, hey, I just need someone to tell me what 3 factorial is, and once you do, I'll multiply that by 4, and now I'll have 4 factorial. So if that becomes kind of our method or our intuition for solving this problem, then what we got to do, so right now the point that we're trying to show here is that, like, right now our factorial function is not equipped to handle any number except 0 or 1. So one of the things we could actually do is we could actually start saying, okay, well, at some point then we need to call the factorial function on itself, but we need to change the input so that we're getting smaller and smaller each time, right? 5 factorial is 5 multiplied by 4 factorial. So here, all we're saying is, great, at some point we know we need to call 4 factorial, right? We need to pass in 4. We need to call factorial, and we need to pass in 4. So let's see what happens there. And now, when I look at result here, the reason why we still get the undefined on the second printout is because the function doesn't, console log on line 12, we do factorial of 2, okay? Factorial of 2, if I step through this function now, it's going to say, okay, is num 0 or 1? Nope. So we skip lines 3 through 5. We skip our if clause. And then on line 9, it says, oh, call factorial of of 2 minus 1, which is factorial 1. Well, factorial 1, if I now start another iteration of my factorial function, I say, what's factorial 1? Factorial 1 returns 1, and that's what we console log, right? But what does factorial 2 return? Well, if I look at factorial 2, there's no return statement, right? On line 9, I do a console log, sure, but I don't return anything. And so therefore, I by default return undefined. And on line 13, when I console log out the result, when I console log out what factorial 2 returned, I get undefined. Okay, so this is a very dangerous or very common trap, and also very dangerous thing to make when you're writing a recursion loop, is that if your loop is supposed to return something, you need to make sure that at every single step it returns something. Okay, now before we return it, we just kind of want to finish the concept first. Is this idea that just to build upon what we said earlier, which is that like 5 factorial is just 5 multiplied by the factorial of 4. Well, now here on line 8, we say, well, if I know how to call factorial of 4, which is this factorial of num minus 1, well, let's just multiply that by ourselves, and now we should actually be kind of done getting the mathematical part of this function, right? So rather than doing a console log, because we know every instance in which we call factorial, we're expecting the previous thing to return a number to us. All I have to do is now in line 8 is we say let result equals num, the number we're dealing with right now, multiplied by the factorial of itself minus 1, and then we return the result. And that's pretty much it. So now when I call factorial of 2, the way that the function is gonna run is the first time if we had a call stack here, as you guys can imagine, the first function in our call stack is now factorial of 2. We go through, we check is num 0 or 1. No, it's not. Great. So we go to line 8 now. And we say result is equal to num, which is 2, multiplied by factorial of 2 minus 1, which is just 1. In order for us to do that line of code, to finish calculating the line of code, we need to first figure out what factorial of 1 is. So on our call stack now, we add in factorial of 1. And so in factorial 1, we go into the function now. On line 3, we say, is num equal to 1? The answer is yep. So then on line 4, we say, let's just return 1 then. And now we're done with factorial 1. We return that 1 to where factorial 1 was called, which was in factorial of 2 on line 8. We replace factorial of 1 with 1. And then we say let result equals 2 multiplied by 1. So result is equal to 2. And then on line 9, we return result, we return 2. And that's what gets printed on, or that's what gets stored as the result variable on line 12. And when we console log out result, we get 2. Okay, so if I was to do this for factorial 5, once again, when we first start our call stack, we have factorial of 5, and we go through this entire function, and eventually at some point we get stuck on line 7 to say, hey, I'm trying to calculate the result variable. It's equal to 5 multiplied by factorial 4. Before I finish this line of code, I need someone to tell me what factorial 4 is. So we put factorial 4 in our call stack, and that says, hey, I can figure out what factorial 4 is, but I need someone to tell me what factorial 3 is. And so we do this process all the way until we get to factorial of 2, and 2 says, hey, I didn't know what factorial of 1 is. So then we put factorial of 1 in our call stack. And then when we run the factorial function, factorial of 1 says, oh yeah, I don't need to call anyone else. My answer is 1. That's pretty much it, and I'm done. So we know that factorial 1 is equal to 1. We can take factorial 1 off our call stack because we got a final value out of it. And now we replace whoever called factorial 1. Well, it was factorial 2. And once we tell factorial 2 that factorial 1 is 1, it says, oh, great, my return value is now 2 times 1. It's just 2. And so we return factorial 2 to whoever called it, which was factorial 3. And that's going to say, oh, my value of factorial 3 is 6. Who needed me? Factorial 4 needed me. And when we give 6 to factorial 4 says, oh, great, now I know that my value is 24, and then it passes back to 25. And the very last step, we can say that factorial 5 is 120, because we finally figured out what factorial 4 with, which requires us to do factorial 3, which requires us to do factorial 2, and so on and so on. Okay, this is pretty much the basics of recursion. So you can see how like, yes, we are calling ourselves, but the point here is to say like, I'm trying to solve one very simple problem. I just need to do it multiple. I just need to do it many times. But each time I do it, I want to change the input just slightly. Okay. Now, I know the way I just described that makes it sound like it's a for loop. And for a lot of the workshop problems for today, you are able to do these problems with for loops. Okay, you are able to write them with for loops, but we are just asking you for the sake of practice to write it with recursion, because in the next workshop, you'll see a whole host of problems that you will not be able to solve with for loops, and you can only solve with recursion. So for the sake of practicing these concepts, I know this right now it seems like more of a pain than it's worth, but it is something that you will need to kind of get a good grasp of. So once again, the takeaways here: write your base case, test it on simple inputs first, and then gradually move outwards as you can, just to make sure they can handle more and more complex inputs. The Chrome debugger exists, and I will do a quick tutorial of it at the end of the second workshop. I think for now, if I introduce it, it probably will cause a little more confusion. It's just a tool, and there's nothing that debugger can do that a few console log statements can't also do for now. So I will cover that at the end of the second lecture. Yep. So this is just saying that a lot of times we may there's a few like certain instances where recursion and iterables may both be useful. But like I said, we'll cover more of this in the afternoon lesson. A few other hints: start with a base case. Start with a simple input first. Always know what you're returning at every single point. Okay. That third point there on line 6. In almost all cases, whatever your base case returns should be the same type of thing that your recursive function returns. Okay, and like with our factorial function, we saw that base case returned a number of 1, and our recursive function returned a number as well, right? And that's just like a very common pattern. It may not always be true, but in the vast majority of cases, it should be true. And then console log or debugger work equally well. I would stick with console logs for now. And then lastly is, if you get really stuck on a problem recursively, feel free to write it out in a normal for loop. Feel free to write out iteratively first, and then through looking at that, you can then probably figure out a way to kind of translate that into a recursive call. One thing not to do with recursion, I notice groups tend to do it because it feels like a bit more of like a crutch, is to say, hey, let me have a variable that exists outside of my recursive function, and then I'll write a recursive function that just edits that outside variable, that global variable almost. That's not proper recursion, because proper recursion, typically speaking, for our workshops, when you do a recursive function, it should exist solely by itself. There should not be an external variable that you're modifying that exists outside of the recursive function. Okay. So you'll know what that means once you start looking at some of the problems, and me and the fellow will bounce through from room to room, and we'll let you know if we see basically following like the global variable anti-pattern. What the global variable anti-pattern means is like for example, if I was to do the factorial problem, if I was to use a global variable, I could say I could have a variable called let total equal 1 that exists outside of the factorial function. And at every instance, all I'm doing is factorial. All I'm saying is total equals total multiplied by factorial of 1 minus total, right? In that case, we have a function that exists outside of the factorial function, and we don't want that. We want everything. We want all the variables that we're going to use to be contained inside the factorial function. Okay, so a lot of talk. I think some practice will probably do best in terms of teaching some of these or making these ideas a bit stickier. Before I do that, any questions?
I'm going back to that very last factorial slide. I have one quick question on that one.
Go ahead.
So just in regards to the logic about that, once you get to factorial number 1, the if statement on line 3 will actually return true, and then you're going to return 1. How does that affect the ability to return the result?
It doesn't, right? Because in every function, as soon as you hit the return statement, that function is over with. Right? Like if num is 1 here,
Mm-hmm.
as I step through this function, if num equals 1, I return 1. Once I do return, once you hit a return, every function can only return one thing, and then once I do the return 1, my function is over with. The computer doesn't even the computer doesn't check lines 5 through 8 anymore.
Right. No, because it's going to then return that 1 for back to line 7 kind of at the end after you've done all of the other factorials.
Yep.
Got it. Thank you.
Yep.
Is the base case always going to be like in an if statement?
In most cases, yes, but it doesn't have to be. But in most cases, yes. I mean, especially for the ones we're doing today, it probably will be because it's just like a nice check to be like, oh, if this is true, then we stop, right? I say it doesn't have to be because there are always like creative ways to write code in which like you're checking something that's like different. So there's no hard and fast rule that has to be in an if statement, but like conceptually and probably for today, you can think of it that way.
Okay.
About the factorial example, from what I understood at the very end that you mentioned not adding in a variable external to the recursive function. This factorial example would make it so that there's no need to have an external variable that saves each factorial
Yep.
input. Okay.
Right. See it.
Kind of my impulse is to be like, well, how is it storing each of these? And is that just kind of what the recursive, like the beauty of the recursive function?
Yep. Exactly. Yeah. Just if you ever think you always need a global variable, just look at this page here, right? We have a factorial function, and all we're ever doing is console log out factorial 5. We never create any other variables here. Yep. Okay. Well, if there are no other questions,